Okay, I need to talk a little bit about Le Chatelier's principle. Le Chatelier, obviously French by the name, was a chemist, physicist, back in those days, all physicists, it seems. But he studied equilibrium systems, and he realized that if he had a system that was at equilibrium, when he disturbed that system by changing its concentration, pressure, or temperature of the species within the reaction system, the system responded by shifting its equilibrium position in a direction that counteracted the disturbance. So basically, the system had already reached an equilibrium state or a steady state, and he made some adjustment to it. He changed the concentration in a reactant or a product. He compressed the system or expanded the system. He changed the temperature. When he did this, what it did was cause the system to adjust itself and establish a new equilibrium. So common stresses include change in concentration, change in temperature, K is affected by this, change in volume and pressure if gases are present. Addition of a catalyst to an compound, though, did have no effect, and we will talk about that a little bit as well. So let's go ahead and apply it. First, let's look at temperature effects. When you have an endothermic process, endothermic again means heat goes into the system. So Q is positive, the heat is positive, delta H is positive. I would also say the system is cool to touch. These are all ways to say a reaction is endothermic. I want you to treat the heat as a reactant. So write reactants plus heat on your reaction. If you treat the heat as a reactant, it can help you identify what's going to happen when we adjust or change the equilibrium. So which direction does the equilibrium shift if the temperature is increased? I have added more heat to the system. This system needs to now counterbalance what you just did to it. You've made the reactant side heavy. The way it's going to adjust for that is it's going to produce more product. So it's going to shift towards product formation. I've added heat, which is a reactant. So in order to counteract that, it's going to take some of that reactant and some of the other reactants and make more product. Which direction does the equilibrium shift if the temperature is decreased? I've removed the heat. Now I don't have enough heat to sustain the equilibrium that's currently existing. What's going to happen is the products are going to react to make more reactant and more heat. Because again, in the forward direction, it's an endothermic process. But that means the reverse direction is exothermic, meaning it releases heat. So the reverse direction will release that heat back at us. So this will shift to the right, to the left, or as we say, reactant formation. What happens to Kc if the temperature is increased? Well, let's think about this. I increase the temperature, which means I make more product. I know Kc is my products over my reactants. I've now increased my numerator and decreased my denominator because some of my reactants are going to react to produce more product. So Kc increases. I have more product than reactant now. And Kc, if the temperature is decreased, if heat goes down, I'm going to form more reactant by consuming some of my product, so my Kc will decrease. If I have an exothermic reaction, again, exothermic, Q is negative, delta H is negative. System lost heat to surroundings. System is hot to touch. always to say that. I'm going to treat heat as a product. I'm going to write the heat in as a product in the reaction because it is producing the products and heat. So which direction does the equilibrium shift if the temperature is increased? I've increased the temperature here. I'm adding more heat. This throws students off. It's like, but it's already giving off heat. You're right. But that means that the reverse direction is endothermic. I add heat, it's going to establish or reestablish itself by pushing the reaction the other direction. So it's going to shift to the left. Reactant formation. If I decrease the temperature, I've now taken away some of the product, so the reaction is going to proceed in the forward direction or move to the right and produce more product. Again, if I look at KC, products over reactants. So what happens to KC if the temperature is increased? I've increased the temperature. I'm going this direction. I'm increasing reactant formation, decreasing product formation. My KC decreases. And if the temperature is decreased, I've decreased the temperature. I need to make more product now. Product is going to increase, reactant is going to decrease, KC is going to increase. Now, I did mention this previously before, but there's two principles that we need to consider here. Compressing a gas favors the side with fewer molecules of gas. If I have a reaction and it's got gas molecules in it, if I compress that system, that means the particles have less space to be in. They're going to adjust by moving the equilibrium to the side that has less gas molecules because then it's less collisions happening. The particles are feeling less pressure. So compression, I increase the pressure. I see I'm favoring the side with, I'm going to shift to the right here. I'm going to favor the side that has fewer gas molecules. If I decrease the pressure, I'm going to actually favor the side here where I have more gas molecules. The reaction will shift to the left because now I have more space for them to be in. It's going to favor the side that's going to form more gas molecules. The second principle, though, is that addition of a non-participating substance or catalyst does not affect the equilibrium. If I add something to the reaction mixture, say helium gas, that's usually the most common example we use. Helium gas doesn't react with anything. It's not going to do anything. It's just there. It's not going to affect the equilibrium. And this throws students off, so like, but you're adding more gas to the system. I am, yes, but I'm not affecting the individual partial pressures of the gas molecules that are involved in the reaction, so it will have no effect on the reaction. And a catalyst, remember what catalyst is, we talked about that. Catalyst is just a way to speed up a reaction by finding a different reaction pathway or a different reaction mechanism to get to our end result. Catalysts are not actually affecting, they're affecting the rate of the reaction, but they're not affecting the equilibrium of the reaction. So neither of those will have any effect on the reaction itself. Let's look at some specific examples. I've got N2 gas plus 3 moles of H2 gas, give me 2 moles of NH3 gas. And as written, the delta H of this reaction is negative 92.4 kilojoules. Because it is negative here, that means it's exothermic. So I'm going to say plus heat on the product side. I'm going to do that right away because it's going to help me identify which way this equilibrium is going to go. What if I increase the concentration of N2? I've increased the concentration here. What's going to happen? The reaction is going to adjust, the equilibrium is going to adjust and make more product. It's going to be product favored. Or shift to right. Because again, the right is where the reactant or where the products are. It's going to take that product, a reactant, and adjust to make more product. What if I increase the concentration of NH3? Well, then it's going to shift to the left. And it's going to make more reactant. If I decrease the concentration of NH3, now I don't have enough product. The reactant is going to react to produce more of that. It's going to be shifting to the right, producing more product. What if I increase the total pressure of the system by compressing it? Now I need to look at the number of moles of gas on each side. Here I have 1 plus 3, 4 moles of gas. Specifically gas molecules. Here I have 2 moles of gas. It's going to go to the side. By compressing it, it's going to the side with fewer gas molecules, so it's going to shift to the right. What if I increase the total pressure of the system by adding helium gas? Helium gas is a non-competing substance. So it will have no effect. What if I increase the temperature? Well, I know heat is a product. I'm increasing the temperature here, which means I'm shifting the reaction the other direction. It's going to go to the left and produce reactants. If I decrease the temperature, my heat's a product. Now I take away one of my products. I need more of it. It's going to shift to the right and produce products. And catalyst, no effect. Okay, what about this example? Considering the following system at equilibrium. CO gas plus 2 moles of H2 gas react to produce 1 mole of CH3OH. So carbon monoxide reacts with hydrogen to produce methanol. What's going to happen here? Well, first I want to look at my delta H here. I'm told my delta H is a negative value, which means this is an exothermic process and this is plus heat. What will happen to the concentration of methanol specifically? So I'm not looking at all the species overall. I'm just looking at the concentration of methanol. Methanol, again, you may not know what methanol is, but you should know the rest. You should know this is carbon monoxide. Hydrogen gas. So even if you can't remember, by default, you should know this is methanol. So I've increased the pressure of CO. I increase the pressure here. It's going to adjust by pushing the reaction the other way. The concentration of methanol will increase. If I decrease the pressure of H2, I've taken away one of the reactants. The system needs to equilibrate by making more reactant, so therefore my concentration of methanol will decrease. The total pressure is increased by addition of helium gas. This is a non-competing substance. So will have no effect. The reaction mixture is compressed. I need to look at the number of moles of gas on each side. 1 plus 2 overall 3 moles of gas versus 1 mole of gas. If I compress this, it's going to increase the concentration of methanol because methanol only has 1 mole of gas on its side, while there's 3 moles of gas on the other side. If I increase the temperature, I'm adding heat to the reaction. Heat is already a product, so it's going to shift the other direction and decrease the concentration of methanol. Lastly, catalyst is added. Catalysts have no effect. So I hope this helps. I hope this makes sense. In the next module, there's a lot more practice. So the next module is just going to go through more examples of working equilibrium examples, working Le Chatelier examples, etc.